So now we're looking at logarithmic functions. So let's go back and let's look at our exponential function. We talked about what the general shape of our exponential function, y equals b to the x, was when b was greater than 1. We got the exponential function looked similar, or had the general shape of the following. And we saw that if b was between 0 and 1, just a reflection across that y-axis, which will look similar to this. We talked about inverse functions last class period, and in order for a function to have an inverse, it had to be a one-to-one function. And this is a one-to-one function. It passes that horizontal line test. So we know that an inverse function exists. We could actually graph the inverse function knowing that the graph of a function and its inverse, recall, were symmetrical to one another across this line y equals x. So if I looked at this, folded the paper, crossed, what this would look like is, well, it's not really, because it should be over more. More like this. Okay, same sort of idea. So this would be the inverse function. But what is that function? And we could find that function. Recall we said to find the inverse functions, we looked at our original function, which was this y equals b to the x, and we swapped our x and our y values and we solved for y. But if we swap our x and our y value, we get x is equal to b raised to the y power. And so how are we going to solve for y? Well, we don't know how to solve for y. And so we, for mathematicians, not we, came up with a definition. And this is saying that y is equal to the logarithm. So we denote that by log, log, of the same base of our exponential, b to the x of x. So these are identical. So logarithms, all they are the exponent of our base that would give us back x. So some stipulations have to hold true for this. Just like for our exponential function, our base had to be greater than 0. Our base couldn't be equal to 1. Remember, our domain and our range are swapped for our function and its inverse. And so our domain for y equals b to the x, this was all real numbers. And our range was from 0, not including 0, to infinity. So our domain is the range of the inverse function of y equals b to the x. And so our range here Here. Our x values for our domain here, they have to be the same as the range, but with x values. So from 0 to infinity. So what that's telling me is what we are taking the log of has to be bigger than 0. And if I look at my range here of my exponential function, well, it's the same as my domain. Sorry, looking at the range of my logarithmic function is the same as my domain of my exponential function, which is negative infinity to infinity. So it's helpful, given a log equation, to rewrite it in exponential form. So let's look at some examples of doing that. So the next example says change each logarithmic expression to an equivalent exponential expression involving an exponent. And so we have log base 3 of 1/9 equals -2. So the base of our log is the base of our exponential. Base of the log is the base of the exponential. So we have 3. Logs are just exponents. So what we were equal to, this y value, is our exponent. So the -2 is equal to what you're taking the log of, which is 1/9. Which is true, right? 3 to the -2 power, we'd bring that down to the denominator. We'd have 1 over 3 squared. 3 squared is 9, so we get 1/9. But it just wants us to get the practice of rewriting these in exponential form. So now let's say you had log base b of actually of 4 equals 2. So this one actually, when we write in exponential form, we can actually solve this. So rewriting in exponential form, our base b is the base of our exponential, is equal to our exponent. Log is equal to the exponent, so that's going to be the exponent of our base, is equal to what we're taking the natural log of, which is, in our case, 4. So b squared equals 4. So we could actually solve for b here. So take the square root of both sides. We get b is equal to plus or minus the square root of 4. So b is equal to plus or minus 2, except we gotta remember that our base, though, is greater than 0. And so b has to just be 2. What if it was ln of x equals 4? So that is not a 1 and an n, it's an L and an N. Well, maybe you really need to know this. So by definition of that, an ln represents the natural log. So the natural log denoted ln of x is equal to our log base e of x. So if you ever see natural log of x, we know the base of that log is e. Same stipulation, our x value has to be greater than 0. So knowing that our natural log is base e, rewriting this in exponential form, our base of our exponential is e. Logs are just our exponent. So e to the fourth is equal to x. So sometimes they want, or I will want, or my math lab will want you to write these values in exact form. And so in this case, this would be the exact form. And then they might ask you after that to estimate. And so I'm just going to pull up e on my calculator, which is a lot of times above the natural log button. You have to push second. So e to the fourth is approximately, let's round to the nearest tenth, so 54.6. So e, just like pi, is an irrational number. So e is a number that represents approximately 2.718. But irrational numbers, recall, your decimal goes on forever and it never repeats itself. So that decimal is going to go on forever, never repeating. So we talked about for logarithms that our domain, that x value has to be greater than 0. And so let's say we were trying to find the domain of the following. So let's say it was the natural log of 1 all over x minus 5. And this is f of x equals. So we can only take the natural log of a positive number. So we know that 1 over x minus 5 has to be greater than 0. Okay, so we learned how to do this in the last chapter, solving rational inequalities. We get the fraction to one side of the inequality, greater than 0. We write it as a single fraction. That's all done for us. We find our critical values if we're going to do this algebraically, or we could graph this. Either way. If I was looking at my critical numbers, there's no number that sets this fraction equal to 0, but there is a value where we have a vertical asymptote, a value where it's undefined, which is x equals 5. And so things could be changing on either side of our vertical asymptote. It could be either above or below the x-axis, and we can't see that unless we test points. And so we just need to test one point on each side. And so let's look at something smaller than 5. So let's say we look at x equals 0. If we go back in here and we plug in 0 for x, we get -1/5 is greater than 0. No, it's not. This is false. So technically, I know that this is below the x-axis on the left-hand side of my vertical asymptote, x equals 5. So now choose a number bigger than 5. So let's say we choose x equals 6. If we go back in here and plug in 6, wherever we see an x, we get 1 over 1, and that is greater than 0. And so this is true. And so for our domain, we need everything to be bigger than 5. or another way to state that, x greater than 5 or parentheses 5 comma infinity. Technically, just knowing where our asymptote is, you should be able to graph this. We know we don't have any x-intercepts. We don't have, let's look at our y-intercept. So we know that we have this asymptote at x equals 5. We have a vertical asymptote. This is just kind of review of what we were doing. X equals 5. A horizontal asymptote, the degree of the numerator in this case is the degree of the numerator is larger, so it's y equals 0. Our y-intercept we saw was -1/5. It was below the x-axis for everything to the left of 5, less than 5. And we saw it was above the x-axis for everything bigger than 5. And so knowing where our asymptotes are, we should know what the graph of 1 over x minus 5 is. Okay, that was just a review. We really didn't need to do that, but you could have used that to find your domain. Figuring out when that inner piece, that natural log, that 1 over x minus 5 is positive. So let's look at one more. So find the domain of, let's say, f of x equals the square root of the natural log of x. So we have two separate places that could give us problems. We have a radical, an even powered radical. So we know what's underneath that radical, this natural log of x. This has to be greater than 0. And x has to be greater than 0 because we can't take a natural log of a negative number. Well, that's a great question. When is our natural log of x greater than 0? Okay, well, let's look at that. Let's actually talk about the graph of the natural log of x right now. Okay, so my computer just, I looked up and you guys were gone. So let me just pause this for a second. Okay, so the computer kind of froze and I dropped the video. So We are graphing natural log of x. I rewrote my natural log of x in exponential form, and now I'm plugging in values for y instead of x to figure out what x would be. So if we plugged in 0 here, I would get e to the 0 power, which I know any number other than 0 to the 0 power is 1. If I plug in 1 for y, I get 2.7 approximately. If I plug in 2 for y, so e squared, that gives me approximately 7.4. Let's plug in a -1 for y. So e raised to the -1 power, that's 1 divided by e, which gives us approximately 0.4. Let's do one more. How about -2? So e raised to the -2 power gives us approximately 0.1. So if we graphed this, at 1 we have 0. At 2.7 we have 1. At 7.4 we have 2. At negative or at 0.4 we have -1. So just estimate. At 0.1 we have -2. And so we get this graph that looks like this. And so if I'm looking at when is my natural log bigger than 0 or equal to 0, it actually can equal 0 because we can take the square root of 0. This is changing at x equals 1. So this is for 1 bigger than, or 1 to infinity, or x greater than or equal to 1. But this is an and statement. This has to hold true and this has to hold true. So you're looking at what they share in common. And so what they share in common would just be 1 to infinity. So the domain is 1 to infinity. Just really quick about the graph, this y equals the natural log of x. This right here is the general shape of the log base b of x if b is greater than 1. So notice that our domain are 0 to infinity. Our range is -infinity to infinity. We have that point 1, 0 is on the graph, which makes sense because that point 0, 1 was on the graph for its inverse function. Remember, x and y swap. And this is strictly increasing. And we have a vertical asymptote at x equals 0. Okay, so we'll look at graphs of logs a little more, and we'll look at when the base is between 0 and 1. But let's first take a break. So jumping into graphing, continuing to graph logs, we looked at the general shape of what the logarithm would look like if our base was bigger than 1. So now let's look at a case where our base is between 0 and 1, and let's see what our graph would look like. So let's say that we had maybe the function f of x is equal to log base 1/2 of x. So another way we can write this, right? Y equals, if we wanted to, if that helps you, log base 1/2 of x. Exponential form, are taking our base of our log, which is 1/2, we're raising it to what was on the other side, y is equal to x. Again, if we plot points, but this time instead of choosing values for x and solving for y, we're going to do the opposite. We're plugging values in for y and solving for x. So if we let y equal 0, 1/2 to the 0 power is 1. If we let y equal 1, 1/2 to the first power is 1/2. If we let y equal 2, well, 1/2 times 1/2, that's 1/4. 3, I got 1/2 times 1/2, which is 1/4, times another half is 1/8. Let's look at negative exponents. So if you have an exponent to the -1 power, that takes what's inside our fraction and flips it. And so that's going to give us 2 to the first, which is 2. Let's take what's in the fraction 1/2, flip it. That would make our exponent of -2 positive 2. So then 2 squared is 4. So let's take what we have and plot our points. Okay, so we have a point at 1, 0. We have a point at 1/2, 1. We have a point at 1/4, 2. Excuse me. We have a point at 1/8, 3. We have a point at 2, -1, and 4, -2. So the general of our shape of our graph for our base between 0 and 1 is going to look similar to this. So notice that this graph, again, we have a point at 1, 0. Our domain, our values from 0 to infinity. Our range, we're looking at numbers from -infinity to infinity. We still have a vertical asymptote at x equals 0. And this one is strictly decreasing. Okay. So being able to recognize what the general shape of the graph is helpful. And then you can start applying some of the transformations to some of the graphs, or to graph them, that we learned previously in the semester. So let's look at a couple of graphs. So let's say we wanted to graph using transformations. F of x is equal to 3 plus log base 3 of x plus 2. Actually, there's a lot more than just graphing it. So let's actually look at all these problems. So with this equation, it wants us to find our domain. So finding the domain, we look for our trouble spots. Doesn't have a radical, it doesn't have variables in the denominator, but we have a log. So that's another trouble spot that we're now going to be looking at. And so we can't have a log of a negative number. And so we know that x plus 2 has to be greater than 0. And so let's solve for x. It's linear, so we can just isolate our x, subtracting 2 on both sides. We have x's has to be greater than negative 2. And if it wanted it in interval notation, then we would do a bracket. We're starting at x equals negative 2 and including it. That's why it's a bracket and going to infinity. Part B wants us to graph this. We can think of this with transformations if you want. We have that plus 2 inside the parentheses. This plus 2 is shifting the graph. This is a horizontal shift, and so opposite for horizontal. So we're going to shift it to the left 2. The plus 3 out here. This is a vertical shift. So we're going to shift this log base 3 of x plus 2 up 3 units. If we want to think about points and what we're doing to get our graph of f of x, we can do it this way. We could plot points. There's just so many different ways we can do this. So if I'm going to shift everything to the left 2, that means that I'm affecting my x value and subtracting 2 from it, from my original parent function log base 3 of x. And then I'm shifting this up 3 units. So y plus 3. So think about these as points. And again, if it helps you to rewrite this in exponential form, then we can. This is 3y equals x. Those are equivalent statements. Back and forth we can go. So I know if x is, I'm sorry, let's do y. If y is 0, 3 to the 0 is 1. So let's look at our new point. Subtracting 2 from our x value, 1 minus 2 is negative 1. And adding 3 to my y value, I get 3. If we plug in 1 for y, we get 3 to the first power, which is 3. So we have a 0.31 on our original function with a shift. 3 minus 2 is 1, and 1 plus 3 is 4. We have a point at 1, 4. We can plug again another value. If we square 3, we get 9. So our new point is 9 minus 2, which is 7, and 2 plus 3, which is 5. Probably should get at least 1 negative in there. So if x is, or y is negative 1, x is 1/3. So 1/3 minus 2. 1/3 minus 2, which is the same thing as 6/3, is negative 5/3. And adding 3 to negative 1, we get back 2. Okay, so I think we have enough to see what that graph of f of x is. Let me move it over. So when x is -1, we have 3. When x is 1, we have 4. Okay, so when x is 7, we have 5. And -5/3. So that is -1 2/3. We have x is 2. Sorry, y is 2. So right now it's looking like this, and I don't know where my y-intercept is, but I could find that technically, right? And I don't know where my x-intercept is right now. But I do know by vertical shifts that my vertical asymptote, horizontal shifts, my vertical asymptotes was at x equals 0, and we shifted things to the left too. So I now have a new asymptote here. So this is going to be hugging this as we come down. So from the graph, determine the range and any asymptotes of this function or of the function. Well, the range. Okay, so range, the range is, for logs are always -infinity to infinity. So our range is -infinity to infinity. And our vertical asymptote that we just mentioned was x equals -2. And then it says part D, so that was part C. Part D wants us to find f inverse, the inverse function of f. Okay, so let's take our function f of x and let's look at the inverse function. Again, f of x was equal to 3 plus log base 3 of x plus 2. Okay, so to find f inverse of x, let's rewrite this as y equals. First step was to swap your x and your y values. So if we swap x and y, we can rewrite this equation as x is equal to 3 plus log base 3 of y plus 2. So now we want to solve for y. So let's isolate the term that has y in it. And so let's subtract 3 on both sides. We would get x minus 3 is equal to log base 3 of y plus 2. Okay, so now what we're going to do is we're going to rewrite this in exponential form. So rewrite this in exponential form. So the base of our log, which is 3, is the base of our exponent. So that's 3. Logs are always equal to your exponent. So in this case, our exponent's going to be x minus 3 equals what you're taking the log of, which was y plus 2. So now that we've rewritten this in exponential form, we can easily solve for y by just subtracting 2 on both sides. And so we get y is equal to 3 raised to the x minus 3 power minus 2. So now we have our f inverse function. So that was part D. Part E, use f inverse to find the range of f. That's bizarre. Thought we already looked at the range of f and then graph f inverse of x. Okay. So let's look at the graph of this. Well, there's multiple ways we can do this, but we already graphed the original function. So recall that, again, that functions and their inverse functions, point on a function, just swap your x and y, that would be the point on your inverse function. And so knowing that, again, we could go back up to our graph here somewhere. We know these points. I'm going to grab them. We know those points, so we know the points on the inverse function. Okay, so now we know that f inverse of x, that point that was on the original -1, 3 is now 3, -1. My point on the original 1, 4 on my inverse function is 4, 1. 7, 5 becomes 5, 7. And -5/3, 2 becomes 2, -5/3. So we can graph that. So when x is 3, y is -1. When x is 4, y is 1. When x is 5, y is 7. When x is 2, y is -5/3. Mine kind of looks off, I believe. Let's see. something looks off. Let me just think about this for a second. And that could just be my tick marks. Okay, so just rewrote what my inverse function was, and what we do have was looking right. I'm just kind of now thinking back to just what I know about this function, my inverse function. I know what my general shape of 3 to the x looks like, which is this. And so that -2 is shifting that horizontal asymptote, which is normally the x-axis, down to -2. And that -3, which my point was normally here, is shifting it to the right 3 units. So what I'm getting looks accurate. Oops. Okay. So if I was looking at the range of my inverse function, this is going to be everything bigger than -2. Or in this case, those are our y values. Y is greater than -2. My domain for my inverse function is all real numbers. Okay, so let's move to solving some of these logarithmic equations. So let me pull an example out. Let's say we have log base 5 of x equals 3. And it says solve each, it just says solve each equation. So let's look at the domain first. Our domain, our values of x have to be bigger than 0 because we can't have a log of a negative number. And so if we ever get a value for our solution that doesn't work, then we need to exclude it from our solution set. So it's possible that when we're solving these, we might get answers that actually are not solutions. And so we have to check. So for log equations, let's just rewrite this. It's in the form that we can just rewrite it in the exponential form. And so our base of our log is 5, which is the base of our exponential. This is equal to our exponent. So 5 cubed equals x. Okay, so from there, it's easy to see that, well, x then is 5 times 5, which is 25, times another 5, which is 125. So x is 125. 125 is bigger than 0, and so we're okay. So if we had log base 2 of parentheses 2x plus 1, this is equal to 3. So again, let's think about our domain, and that maybe if we keep doing that, then maybe we'll remember that we have to check when we start getting these values that don't work. And so our domain, well, what we're taking the log of, in this case, is 2x plus 1, has to be bigger than 0. Okay, it's a linear inequality, so we can just solve it like it's an equal sign. And the only thing we have to worry about is dividing or multiplying by a negative number, and that would flip our inequality, but we're not going to be doing that in this case. So subtracting 1, we get 2x is greater than -1. Divide by 2, we get x is greater than -1/2. Okay, so to solve this though, let's rewrite this in exponential form. So our base of our log is the base of our exponent, 2, equals, this is equal to our exponent, 3, equals 2x plus 1. Okay, so this is a linear equation and we know how to solve that. So let's just simplify the right-hand side or left-hand side, which I'm going to write on the left, right? So I'm going to rewrite this as 2x plus 1 equals 2 cubed. Simplify that, that's 8. Isolate x, subtract 1 on both sides, we get 2x is equal to 7. And divide by 2, we get x is equal to 7/2. 7/2 is bigger than -1/2, so it works. And our solution would be 7/2. Let's say we had log base 6 of 36 is equal to 5x plus 3. So in this case, where my variable is, I don't have to worry about the domain. I already have that log of 36, which is a positive number. So again, we want to rewrite this in exponential form. So the base of our log is the base of the exponent, which is 6. Log are always equal to the exponent, or just exponent. So our exponent of our base is going to be this 5x plus 3 equals 36. So this brings us to what we were doing at the beginning of the class, where we had to manipulate the bases to be the same in order to set the exponents equal to each other. In 6 and 36, we can manipulate those bases to be both 6. So we have 6 raised to the 5x plus 3 power equals, well, 36 is the same thing as 6 squared. So now we can say, okay, we got the bases the same, so our exponents, 5x plus 3, have to equal 2. So let's solve for x, subtract 3 on both sides. We get 5x equals -1. And then x is equal to, divide by 5, -1/5. Which, if you plug in back here, because you really should know, this is 6 to what power equals 36. So this should give me back 2 when I plug in -1/5, and it does. 5 times -1/5 is -1 plus 3, which is 2. So let's go in the opposite direction. Let's say that the equation it gave us to solve was an exponential, but the bases can't be manipulated to be the same. So for instance, let's say we had 2 times 10 raised to the 2 minus x power is equal to 5. Okay, we cannot multiply that 2 times 10. That is illegal. It's not in our order of operations. Order of operations says we have to deal with our exponents first. And then we have to, then we can multiply. And so I can't say that that's the same thing as 20 raised to the 2 minus x power. So don't do that. So let's first isolate this exponential piece. So let's get rid of the 2 in front, and we could do that by dividing both sides by 2. So doing that, we get 10 raised to the 2 minus x power equals 5/2. So normally I would do this by using logarithms and taking the logs of both sides, but we haven't really dealt with that yet, and using properties of logs. And so we could deal with this by going backwards because we want to get x by itself. So let's go backwards. And remember, logs are just exponential problems. And so we're going to look at this and rewrite this as a log. Okay, so log of the base. Well, the base of our log is going to be the base of our exponential. So we have 10 here. Log of, so that's our answer, 5/2 here, equals, this is always equal to the exponent. So our exponent in our case is 2 minus x. We're almost there. We can get x by itself. We could subtract 2 and then multiply by -1, or I could add x to both sides and subtract this log. Either way, we'll get the same result. So we would get, we get -x equals, let's subtract 2, log base 10 of 5/2 minus 2. Multiply both sides of our equation by a -1 to make that positive 1x. So doing that, we get x is equal to, and I'm going to write the positive number first. So positive 2 minus log base 10 of x. I haven't stated this yet, but if you have base 10 of your log, we don't write that. So we just say log of x. So if you ever see a log without the base, then it's base 10. So log base 10 of x is just equal to writing it as log of x. So I've actually seen students do it this way before, and I thought, okay, well, why are they doing this way? Because I've never taught it this way. I've always waited until we've looked at properties of logarithms. But I also realized what they were doing was correct. But here's, and I'm seeing it in a book where it's being taught this way too. So that was interesting to see. So let's look at one more. How about log base 2 of 8 raised to the x power equals -3. So again, solving the equation. We want to rewrite this in exponential form. And so our base of our log is the base of our exponential equation, which is 2, is equal to, so this -3 is our exponent, -3 equals to what we're taking the log of, which is 8x. So here's another case where we can manipulate the bases to be the same. We can rewrite 8 to be 2 cubed. So you have 2 to the -3rd power equals 2 cubed, and then that's raised to the x power. But power to power is multiplication of exponents. So we get 2 to the -3rd power is equal to 2 to the 3x power. Bases are the same, so we can set our exponents equal to each other. So we have -3 equals 3x. Divide through by 3, we get x equals -1. I'm not, if I plug this back into my original, I'm never gonna, it's gonna be okay because it's gonna be a log of base 2 of 1/8, which is a positive number. 1/8 is. Okay, I lied. I said this. Let's just do one more. Oh, this is a good one. We still have a few more minutes. I might as well throw in a couple more if we have time. So what if it was, where did it go? That was a really good problem. The natural log of e raised to the negative 2x power is equal to 8. So recall, natural log is log base e. We haven't talked about this property yet. So if we go backwards and we think to ourselves, e to what power gives me e to the negative 2x, it's just negative 2x. But if I didn't see that, we could go and we could rewrite this in exponential form. So the base of my log, the base of natural log is e. Raise it to the other side of the log, which is 8, equals what we were taking the log of, which was e to the negative 2x. So notice we have the same base in here in our exponential equation, so we can set our exponents equal to each other, and we have 8 equals negative 2x. Divide through by negative 2, we get x is negative 4. If you had seen what I was talking about before, you should know that the natural log of e to the negative 2x, again, is just negative 2x. Negative 2x equals 8. If I divided both sides by negative 2, I get x is negative 4. We'll talk about that property next week. One more. Let's say we were started instead with an exponential again. So e raised to the negative 2x plus 1 equals 13. So I can't manipulate e and 13 to be the same base. And so let's rewrite this in log form. And so base e, so this would be natural log or log base e of what this was equal to, 13, equals our exponent, which is negative 2x plus 1. So we can solve for x here. Let's subtract 1 on both sides. So I would get negative 2x is equal to the natural log of 13 minus 1. And then divide both sides by negative 2. So x is equal to the natural log of 13 minus 1 all over negative 2. So that would be the exact answer. And for your exam in this section, I don't allow calculators. And so I would just say, give me your exact answer, and this would be it. Okay, so this is the rest of the one section on logarithms, graphing logarithms, solving certain equations of logarithms. We have a few more sections that cover logarithms, properties of logarithms, and going in more advanced of solving equations of logarithms. The next section that we're looking at, properties of logarithms, is something that we're using right now a lot in calculus, where we're taking some ugly function that would be hard to differentiate and using our properties of logs to make it come out so nice and simple. So logs are something that are very helpful in the future math classes, and also I'm sure in your sciences. So let's again stop there for today.